All right, so this last section of chapter 2 talks about piecewise linear functions, right? So we already know how to graph linear functions, right? No problem. Now what we're going to do is look at a function where it's defined literally in pieces depending on what the value of x is, but each of the separate pieces will happen to be a linear expression. So hence the name piecewise linear function. We already know about one, but we never looked at its graph until now. Let's look at the absolute value function. Right? So remember, if I gave you a real number x, the absolute value of x is itself if x is already non-negative. But if x happened to have been negative, the absolute value would have had to multiply it by -1 to return that positive value. Remember, because absolute value gives a distance, if you think about it, from the origin. And so what we can look at though is this is a piecewise defined function, right? That we can actually graph it in the xy plane. So for example, how do I get the graph? Well, if x is non-negative, so you take inputs to the right of the y-axis or on the y-axis, the graph of the absolute value of x is the same as y equals x, right? And so here, I'm going to graph y equals x, right? The point 1, 1, 2, 2, 3, 3, all the way up and down, up the line is on that graph. And so I get this piece. So don't actually worry about this left piece for now. You just get this part of the graph. Now, you don't continue on to the left with y equals x because this part only applies if x is non-negative. All right, so we don't consider what the graph of this looks like for negative values of x. Rather, if x is negative, the graph of this function looks like the graph of y equals -x, which is this line, right? So notice here, I'm only using the part of the graph of y equals -x for negative inputs, right? Because otherwise its graph would have occurred down here as well. But I'm not using positive x values here. I'm only using this graph here when the input happens to be negative. And so if you take those two together, this V-shaped graph is what you call the absolute value function's graph. All right, so we can do the same sort of thing with any number of pieces. That could be 3, 4 pieces if you want, and they don't all have to be just x or -x. You could have constants, you could have 3x, you could have 5 minus 3x, you could have any linear expression you want at this point, and the same sort of tack would apply. So let's take a look at, let's say, this example. Here we have a function that is defined in 3 pieces, and what we want to do is graph that function on the xy plane. Let's just talk about it verbally before we look at the graph. The first piece that we encounter is y equals x plus 4, right? So we know what y equals x plus 4 looks like. It's a line with a y-intercept of 4 and a slope of 1. So if you're gonna, why don't you try to do this along with me on just a scrap piece of paper, just so you can kind of see how you'd construct this. Go ahead and graph y equals x plus 4 in its entirety on the xy plane. Once you've done that, erase the part of that graph that corresponds to x values that are bigger than or equal to 1. Right? So it's going to be a right-hand part of that graph. Literally erase it from the xy plane. You're only going to keep the part of that line that has an input less than 1. At x equals 1 itself, you're going to put an open circle because we're not allowing that x value in the graph at this point. All right. Next, we have a constant, y equals 2. And we know what the graph of y equals 2 looks like. It's a horizontal line because the slope is 0, right? Remember, the slope is the change in y over the change in x. Well, there is no x term. So there is no change in y as the x changes. So it just stays horizontal. All right, so we're going to graph the line y equals 2 in its entirety on your xy plane. And then once you've done that, erase the graph that for x values that are to the left of 1 and to the right of 4. So you're only going to have this little itty bitty little segment, and make a closed circle on that graph when x is equal to 1, and an open circle when x is equal to 4, right? We use a closed circle because we're including the 1 here, and we use an open circle because we're not including the 4 as an input here, all right? And then finally, we have a third piece, y equals x minus 5, as long as the input is to the right or equal to 4. So go ahead and graph y equals x minus 5, again, in its entirety on the xy plane. Remember, it has a y-intercept of minus 5 and a slope of 1. Once you have that graph, erase that part of the graph that corresponds to x values less than 4. Right, so you're only going to keep that graph when x is to the right or equal to 4. Okay, so erase for x less than 4, and then put a closed circle at the graph when x is 4. What you should get is a graph that ultimately looks like this. Ignore the dotted lines. Those are just there for helping us graph. It's basically this purple graph is what you'll get in the end. And that's the approach you take to graph any piecewise linear function. In fact, later on, we're going to look at piecewise functions like this, but we're going to replace the pieces with quadratics, with square roots, with any other function you want, but the same approach is actually going to be used. You just graph this function here for those x values, and then you paste those together one piece at a time to get the ultimate graph. All right, so, well, I already showed you this one. Go ahead and actually try this your turn. It's a little bit tamer than the other because two of them are constants, but see what you get, and then I'll put the solution up just so you can check yourself. All right, so this is the graph that you should get. Notice that it's the constant 2 to the left of 0. So here's the constant 2. I put an open circle at 2 because, or sorry, at 0, 2, because I'm not including x equal to 0 as an input on that part of the graph. Okay. Between 0 and 3, we have the graph of y equals x, right? So there's that. You could have put a closed circle there, right? In fact, you would have initially then realized that it connects at the same point, but in the case, you probably would have at this point put a closed circle on your graph. That's perfectly fine. And then here we want the constant y equals 3, which actually matches up to the point where you stop the other one, hence the lack of a closed point there, since it's continuous. And you get that sort of horizontal graph to the right. All right. Look at the next your turn. All right, so you have now a graph of a piecewise defined function f of x here, and what you want to do is two things. You want to evaluate the y values or the functional values at these particular x values, and then you want to try to find a piecewise definition for the function itself. So an f of x equals to however many pieces you need and what the intervals of the x values are. So go ahead and try that and then we'll talk through it. All right, so for the first part, f of negative 4, does each of these units is equal to 1, right? So negative 4, 2, 3, 4 is here. The functional value at negative 4 is the y value of the point that corresponds to that, namely 2. That's how I'm getting 2 here. Same way f of minus 2 is here. I don't use this guy. You're going to go to where the closed hole is, namely up here to get the functional value. That's 2 as well. F of 3, the same sort of thing. Here's 3. Now the question is, do I use the y value here or do I use the y value there? You only use the y value at the closed hole. And so the y value is minus 3, and so that functional value is minus 3. And then finally f of 5, here's 5. F of 5 is the y value up here, which ends up being 4. All right. Now, to find the piecewise definition, you have 3 distinct chunks there for this graph. And so you're going to have 3 distinct pieces in the definition. Right? Notice that the function's equal to 2. So the y value goes here. That the equation for this part of the graph, which is 2. And the x values for which it holds is everything strictly to the right of minus 5 and to the left or equal to -2, right? Because I have a closed point here, but an open one there. And so the x values for which it holds are those in the interval from -5 to -2 inclusive. Same way here, the next part of our graph is y equals -3. That's where this constant's coming from. And the x values for which it holds goes from -2 not inclusive to 3 inclusive. That's where I'm getting this double inequality. And then the final piece here is up at 4, and it's equal to 4 as long as the x value is between 3 not inclusive and 6 inclusive. Right? So that's how you can generate a definition of a piecewise defined function from a graph. If these happen to have been non-constant segments, so if they happen to have had a slope to them, you'd have to find the slope of that line segment and its intercept, or at least its equation using point slope form, right? So they could be a little bit more involved, but you already know how to find the equation of a line given 2 points, and so you just would have to go through and that process to find the equation of that line to get each of these pieces in that case. Otherwise, it's the same. All right, and then finally, let's take a look at this application problem, right? So step functions are basically piecewise constant functions that go up by a fixed amount each time for a fixed length of interval. So they literally look like a staircase, right? And they come up a lot with hourly rates, right? So for example, let's look at your turn 3. A plumber is known to charge $40 per hour or any portion of an hour. All right, so in other words, she'll charge you $40 up to the end of a first hour, and then the minute you're past the first hour, the charge increases by $40 for the rest of that time. All right, and this keeps happening every hour. And so what we know is that the functional value is going to change at every hour mark, right? So if the x-axis is labeled in hours, then at x equals 1, x equals 2, x equals 3, you're going to have a jump in the graph because the price is changing at those particular times. But between any 2 consecutive positive integers, the y value is always going to be the same, right? Because the charge is a blanket cost, a fixed amount for any portion of an hour. All right, so let's take a look at what that would be. So for the first hour, we're not including 0, because if she's not there at all, she can't charge you $40, right? So it's like she never even came to the door. But the minute she's at the door and she sets foot in, then for any amount of time from then up until the first hour is done, the charge for that amount of time is $40. The minute she's there for longer than an hour, the charge goes up to $80, and that's true all the way through the second hour. Once she's there more than a second hour, the price goes up another $40. And so notice here, the structure is always the same. The jump occurs right at the hour mark, and it occurs strictly to the right of that time. The jump is always by $40, right? And so the graph here, I don't have the graph shown here, but the graph basically would look like, it would be 40 with a open circle at 0 and a closed circle at 1. And then the next piece would jump up to 80, open circle to closed circle at 2. Then would jump up to 120 with an open circle at 2 and a closed at 3, so on and so forth. Right? So you get literally a step-by-step linear function. And then here, how much does she charge for working 3.5 hours? All you have to do is locate where that x value is in which of these intervals. And here it occurs smack dab in the middle of this interval. And so she would charge $160 for such a visit. All right, that's how you use that. So for the homework problems, there are a couple of word problems that you have to work through, right? And then some non-word problems, but they're all basically not too bad. Some of these down toward the end get a little bit worse. So plan to spend a little bit more time on some of these because they're trying to combine concepts that we learned in chapter 1 and in this chapter. So go step by step through them and bring any questions to my attention at our next meeting. All right, take it easy, everyone. Bye. Oops. Maybe.